Okay, so I kind of want to quickly, or somewhat quickly, catch you up to where we got to last week, right? And then still quickly, but maybe less quickly, finish the rest of the problem. Okay, so this problem is kind of an interesting problem. We have this thing called fractional distance. Yeah? Okay. So basically it's the same as like normal distance where you take like vertical and horizontal and do Pythagoras. Yeah? Except the vertical and horizontal go through one more process before you make the triangle. So instead of just taking the difference of the vertical straight away, you then make the distance from that to the nearest integer, and then you carry on. So like if this was like 6.3, then the distance would be 0.3, and then you do 0.3 instead of 6.3. Yeah? And if it was like 9.8, then it'd be like 0.2 to the nearest integer. So then you write 0.2 here. That makes sense? Okay. So some pretty obvious things you can see from this is that this maximum R value cannot be like more than the square root of half, yeah? Because you can only get like half here and then square it, and then half here and square it, and quarter plus a quarter is a half, and you get the square root of a half, yeah? Okay, so you can't ever get more than that. Did you guys notice that yeah, so did you guys notice that I don't know, did you get some, if you put some points there, it's pretty easy to get certain distances? Yeah, Liam, you were here last week for this, right? Alright, so basically, you see if you put a bunch of coordinates in there, if you just deleted all the integer parts, so if you like use 7.3 and 6.9, but you use like just 0.3 and 0.9, you get the same results, right? So what that effectively means is you can put everything in a unit square, right?
Yeah.
From like 0, 0 to 1, 1. And if you do that, you get some pretty easy values. For example, you could put like points at the origin 0, 0. You could put it at 0, half, half 0, and half half, like the four vertices of the quarter square, and then you get the R value is half, right? Okay. So basically, up until last week, I think we had that the R value was a half. Okay. And then we had the belief that it was a half. Okay. But sort of after the lesson, we could prove that the R value is in fact more than half. Okay. So I guess that's like sort of like the first step. So I'll pause it there. So see if you can get an R value that's bigger than half. Okay. That makes sense. Yeah, so I remind you, so we got everything into a unit square, right? And we also got that we can actually move all 4 points, like translate it wherever we want. It won't change the fractional distance. So we can actually, we'll log that one of the points is whichever point we want. And the point we chose last time was like the very middle of the square, half, half, yeah? And then from the middle of the square, if you draw a circle with radius a half, right? That's kind of like the in circle of the square, yeah? And we showed obviously like anything with fractional distance greater than a half from the middle point has to be outside the circle but inside the square, yeah? So that really restricts where you can put the other 3 points. Okay, so we're still looking for 3 points where the minimum distance is bigger than a half, yeah? Once we got that, I'll give you a few minutes more to get that. Okay, so if you look at the this thing here, so I put in the server already. This is a pretty simple idea, okay? So here's the unit square, right? Here's the circle, the in circle that you can't go inside of, right? So one really simple idea is like, so if you want a distance of 0.5, you can make them like vertically 0.5, right? But you can't make them vertically more than 0.5 because 0.5 is the max you can go in one direction, right? But if you make it vertically 0.5 and you make it horizontally anything non-zero, it'll be more than 0.5, right? So for example here, you can try to get this one up here and then you just move that in a little bit, yeah? So now the distance is greater than 0.5, yeah? Okay. Here, the distance here, and also having this across by a little bit actually makes it a little bit easier to fit something up here, right? Because you can't really put it at the top, you can put it a little bit further. Okay, so here's a horizontal distance of 0.5, yeah? So then whatever the vertical is, as long as it's not 0, it's going to have an overall distance more than half, yeah? Okay, and then in this one, the only thing you really need to check is what happens with this one and this one, right? You see, so the distance they have apart is, so it's really 0.3, right? And vertically. And horizontally, it's like 0.45, yeah? And then you just need to check that 0.3 and 0.45, they make something more than 0.5, yeah? Because 0.3 and 0.4 makes 0.5, right? So 0.3 and 0.45 will make something more than 0.5. Okay. Yeah, so I mean, if you look at this example, it's not the most efficient example, okay? So this one doesn't even go above, like if we instead of just, we talk about the squares of the length to avoid like lots of square roots, then we beat 0.25, yeah? But we haven't even gotten up to 0.26, yeah? So maybe just for a couple of minutes, can you see how you can get it to 0.26, okay? So at the moment it's less than 0.26, it's 0.25, it's like 5 units across and half a unit up, right? So can you get it to like 0.26, for example? Yeah. Yeah, so if you look at what does 0.26 mean, right? 0.26 is really, it's 5 up and 1 across, right? So at the moment this is only half across, so it's not even 0.26, yeah? But this could actually move over here and it's 0.26, yeah? This thing is actually more than 0.26 because it's 5 across and 2 down, right? So you can even move that up 1, right? So this one has got the most freedom to move. That one can kind of move, it can't quite move across because it's hitting the circle, but if it goes up, then it can move across, yeah? So basically, if you just make this kind of more symmetrical, you can get it to be 0.26. So if you look at the picture we have, it's like this one here. See? So we put it at 0.1, 0.9, yeah? 0.6, 0.61, and then 0.4. Then all the distances on the outside of this rhombus are 0.26 when you square it, yeah? And it's just the diagonals that are, so this diagonal is like 0.32, yeah? Because it's 4 and 4. And this other diagonal actually, believe it or not, is also 0.4. It's also 0.4, 0.4, so it's also 0.32. That makes sense?
Yeah.
Yeah, so I guess this process, I mean, this is kind of like, if you get too fixed on, see, like one of the things I catch people doing, like we might have done is when we had half, we thought it was like the answer was a half, right? But we had no reason to actually think the answer was a half. If you actually like strip down all the actual reasons we had that didn't apply anymore because we had like a bad start, right?
Yeah.
There was actually no reason to believe it was a half, right? And this proves it's not a half, it's at least square root of 0.26, you know? And even doing this, like you shouldn't be too focused on, oh, I need to get the result 0.26, you know? Like, you're doing it while noticing sort of how things work, yeah? You're kind of understanding how the distances work, okay? So one of the understandings you might have is actually, how does the distance actually work? Well, see, this one looks like it's far from this one, right? But what's the vertical? It's not 0.6, right? It's actually 0.4, right?
Yeah.
And what's the horizontal? It's not 0.6, it's 0.4. So what it actually is it's kind of like Pac-Man. You're allowed to go to the top and come back down the bottom.
Yeah.
Does that make sense? So like the closest distance, it's the closest if you assume sort of the top and the bottom are connected. Does that make sense? So in some sense, then the fractional distance in the problem is the same as the normal distance if you account for this teleporting from one side of the screen to the other.
Yeah.
Okay. There's actually a very nice way to describe this. Maybe you could just for a moment indulge me. So if you identify the left line, right, with the right line, yeah? You know what I mean by identify?
Sure.
So like every point on the left side is equal to the point on the right side, yeah? Because they have zero distance, right? Okay. So then glue it together, yeah? So what shape do you get? You get a cylinder, right? Okay, but the same happens for the top and the bottom, yeah?
Yeah.
Right? So if you say like, if you glued this point like around this way, right? Yeah? Down to here, then you kind of get like, let's say that's going clockwise, for example, right? And then in the bottom one, you're also gluing this way to that way. Okay. Let's say it's also going, so I guess, let's say it's also going clockwise, right? Then when you glue the bottom to the top, you see what happens? Hmm? So can you see what happens if, so the gluing the first one is easy, you get a cylinder, right?
Yeah.
And then you have two circular faces, right? One on the top and the one on the bottom. Like, if you glue those together again, right? Can you see what you get? Yeah, so you get like a donut, yeah? So what we call it a torus, yeah? Yeah, so the torus is like a funny shape. As far as I know, that's how they're trying to make nuclear fusion at the moment with the shape of the plasma thing or whatever. The vacuum, they're trying to get it in like to spin around in a torus and then make high energy or whatever. But like, so basically what we have is like the distance we have in the plane, right, is just a normal distance on torus. Yeah? That's one way to like say it shortly, yeah? But you know, like it might not make you understand it any more than you're just going around both sides freely, right? So like the things which are close, like one's on this side and one's on the other side, they're actually close together because the edge is the same point, yeah? Does that make sense? Okay. Yeah, so now the question is, can you beat 0.26, okay? So if you look at how we did this and sort of our understanding of how to calculate distances, can you try to beat maybe 0.26, okay? I can't give you too long for this, but I'll give you a little bit of time. Okay, so if you look at this situation here, right? We got all the things are 0.26 when you square it, but the red and green lengths are like 0.32, right? So there's like a huge difference between 0.32 and 0.26 in this situation, right? So maybe you can like sort of reduce the red length to try to increase the other lengths. Does that make sense? Okay, so one thing what we did was we kind of moved this point down and across. So we plus like a little x to the x and y values, right? Or subtracted from the y value and added to the x value, yeah? And then we added the same x to the x value here, so that it just kind of, it keeps the 0.5 going, yeah? And then we subtracted the x from the y here to keep the vertical distance the same, yeah? But can you see, because that thing is also going further inwards, this horizontal distance is going to be increasing, yeah? And this vertical distance is going to be increasing. And then the yellow lengths are also increasing, yeah? So if we can actually do that, we'll get something bigger than 0.26, yeah? That makes sense? Alright, so now the question is, how much bigger can you get it? And so Peter had the answer was 2 minus root 3, yeah? Which is like, I think it's still like less than 0.27, is it?
Yeah.
2.26 something?
2.267.
Yeah, so it's still less than 0.27, right? Does that make sense?
Yes.
So you pretty much move this point as far in as possible, yeah? And then these two follow. And so this distance is decreasing, this distance is increasing. And basically when they're equal is probably where the best we can get, right? So in this diagram, because when they're equal, if you keep going, then the one that's getting smaller, it's going to make the R value the smaller value, right? Okay, so if you set those equal and you solve it, is that what you did, Peter?
Yeah, I think so.
You get an R value of 2 minus root 3.
R squared.
The R squared of 2 minus root 3, yeah? Okay. So then the question is, can you do any better than that? Yeah? Okay. The question is, can you do any better than that? Alright? Okay, so if you want to see how we did that calculation, we just did like, so this was 0.1 plus x, right? 0.9 minus x. And then this is like 0.6 plus x. And this is 0.4 minus x, right? And so the distance here is like it's 0.4 minus x and 0.4 minus x to the middle, yeah? So basically trying to solve when that distance, so that's like 0.4 minus x squared times 2, right? When that's equal to this distance here, so that distance there is so it's 0.6 plus x, so that's 0.5 squared, and then the 1 and the 0.9 minus x just makes 0.1 plus x, yeah? And then you can so one thing that kind of helps, you can let x equal 0.1 plus little x, and then you get 0.5 squared plus big X squared equals 2 times 0.5 minus big X squared, yeah? And then here you get the 0.5 squared and the 0.5 squared cancel, so there's only one 0.5 squared. 2x squared and one of the x squareds cancel. And then there's a minus 2x from this. Yeah, is that what you did? And then you complete the square. X squared minus 2x plus 1 equals, this is a quarter, you get 3/4. And so then x minus 1 all squared equals 3/4. X minus 1 is plus or minus root 3 on 2, but it can't be more than 1. So capital X is actually the x value of this point here, okay? So it can't be more than 1, so it has to be 1 minus root 3 on 2. That makes sense? Okay. And then to find the distance, you just do 0.5 squared plus x squared. So x squared is 1 minus root 3 plus 3 on 4. And then 0.5 squared is just a quarter. So when you add that up, you get 2 minus root 3. Yeah. Okay. Okay. So if you play around with it quite a bit, you'll start noticing like there's only certain spots that you can really place points. So I did this kind of like a little map. So this thing's like a little map. If you kind of like, for example, if you look at this corner, like this 0.1 by 0.1 cell, right? Like if you put something there, you can't really put the other points anywhere else, because so you're looking for something which is like, 5 units across and more than 1 unit wide, right?
Yeah.
And 3 and 3 is not going to even cut it, right? 3 and 4 is not going to cut it, right? To be like not like 0.5 across, it has to be like basically 0.37 up and 0.37 across, So if you're in this corner here, right, like where can you even go like 3 in one direction, It's like if you go 3 in one direction here, the further you go, the less you can go vertically, right? So if you go 3 here, then you can't go anything vertically. So, but if you want to go something vertically, like here, then you can't go anything horizontally, right? So if you just kind of look at each of these cells like that, right? Then what you get is you get kind of like this, kind of like 3 openings. There's kind of like 3 areas where you can actually place a point, right? And you can't eliminate those 3 areas because they're the actual 3 areas you used for that construction, right? So so there's no chance of putting any points anywhere other than those 3 points, 3 areas to beat that distance, yeah? And so obviously by symmetry you get it for all the quarters, right? That makes sense. And then with just doing some cases, you can see that like if you put a point, you basically can't avoid putting a point in the middle part, yeah? You can try really hard. So you obviously can with log, you got a point in here, yeah? And then if you got a point here, then obviously you can't put it in these 2, right? But you can still, well, so there was a little bit of a debate about whether you can fit a point here and a point here, yeah? Like if it was just like on the edge or something. It might just be big enough, but I think that ends up with just the same distance we had before, yeah? The same R. And that's like right on the, basically right where we put the 2 points anyway. So like, they'll just have the same R, yeah? Okay. Yeah. So you can put one here, for example, but if you put one here, then you're gonna have trouble putting the next thing, because see, this thing, it looks like it's far away from this, but it's actually really close, you know. And this thing is pretty close to this thing, right? Oh no, this thing is just close to this thing, yeah? They're just like 3 cells apart. So, for example, if you have like something here and something here, right? Think about where you could put your third point. And there's really just, you know, like 1, 2, 3, 4, 5, 6, 7, 8, 9 sort of possible regions, you know? So you can't put it here. So that's what the crosses mean. You can't put it here, you can't put it here. You can't put it here because it's too close to that. And this is basically the same as that, so that's too close as well. This is too close to that, and that's too close to that, right? So you can't put it anywhere except for the middle, yeah? But the middle, you have similar problems as well. If you put one thing in the middle, you can't put anything in any of the other middles, because all the middles are basically the same distance apart, and it's not big enough. Yeah, so if you end up doing these cases, you'll figure out there's basically only like 2 kinds of configurations you can have. It's like the one we had that solved the problem, like the construction from before. It's like here, so BCD basically. And you can also have ABC, okay? So it's kind of a little bit distant, okay? And if you consider sort of moving the points a little bit, okay, then it's actually really hard to keep this configuration stable. So for example, if you have like A, like if A is on the edge of like the R value, right, it can't move right and it can't move down, because then it'll get closer to the middle point, yeah? So it has to move left or up, right? It can't, basically it's already up, so it can only move left. And it can also move left and down, yeah? But see, if it moves left and down, then it's getting closer to B, and so B has to try to move away, right? So, but B can't move left and down because it's gonna get close to the middle. It has to move up. So it has to move up, and possibly up and left, right? But if it does that, then like the point C, yeah, so if it moves up, it actually gets closer to the point C, even though it doesn't look like it, right? It's getting closer from the other side, yeah? So then C has to move to make up for that, but then it's going to start clashing with A now. That makes sense? Okay, so how does this help? Well, so I think how it doesn't help is kind of obvious, because people will be like, oh, how are we going to write that up, right? But maybe it's not quite the point how we're going to write that up. It's more that you've gained certainty that your answer is 2 minus root 3. That makes sense? So once you consider all these cases like this, like you now are sure that the answer is 2 minus root 3, yeah? Whether or not you can communicate that certainty with this kind of write-up, right? That's another story, yeah? But you've gained something, so you can't, like, you might not be able to monetize it right away, you know? But you have like the certainty now, right? Does that make sense? So now it's a question of proof writing, okay? So now you can actually be confident that when you write 2 minus root 3, you'll get the marks for the construction, yeah? Because it's going to be the correct value, okay? But, you know, like, just as you're not satisfied with this, it's not going to be necessarily a satisfactory write-up, right? So now the question is, how can we sort of write this up, yeah? And so there's one little thing that really helps for the write-up, okay? So one thing that really helped for the write-up, so when we took we could log that any point there's one point that's anywhere we want, right? And we chose the middle point, yeah? So there's actually another choice of that point that really helps. So maybe you can think about what other point you could choose to help us, okay? So there's lots of degrees of achievement. There's kind of like, what point is it, okay? Why is it helpful, okay? So just like a rough reason why it's helpful, okay? And then we'll get like a precise proof that that demonstrates actually exactly why it's helpful, okay? Does that make sense? So we're trying now to prove that we're doing the other direction now, okay? And the question is, can we choose another point other than the middle to help us? And which point is it? And why would that point be helpful? Okay? Does anyone want to sort of voice their point? What point would you say? Alon says corner. What does Liam say? Who says corner? Put your hand up. Ryan? Wow, Ryan is like... So we got Ryan and Alon said corner, yeah? Any other points? Okay, so... I mean, there could be other points too, maybe, but if you do the corner, okay? Let me show you the corner. If you do the corner, then the points become like, so so if you take the green point in the corner, yeah? So all the corner points are the same point, basically, right? So now your circles kind of become these weird circles like this, yeah? Okay. So I guess maybe the question I want to ask you is, why does the corner help? Yeah, why is corner maybe better than the middle point? Yeah? So that's the question I'll give you a few more minutes for. Okay. So if you put the corner, it kind of looks like this. The green region is you have to avoid, and you can put stuff in the middle there. Yeah? Okay. All right, so yeah, so one reason it's just like maybe you call it a heuristic reason. It's like, so one of the main difficulties we have is like we have this funny distance, right? It's nice to say you can teleport and stuff, but wouldn't it be nice if it was just like the normal distance, right? So here, if the stuff is close, because the reason how the circle worked, right? It was the stuff inside the circle was all normal distance, right? With the point, yeah. But that's kind of wasted because you never can put anything in there, right? But now you put it on the outside, the region on the outside you can't use, the region in the middle is the one you can use now. And now the points that you're putting on there are in a region where it's kind of more like the normal distance. Yeah? Okay. So I guess the next part of the exercise is, okay, so what we're doing is we're making the circles of radius, like the radius squared 2 minus root 3, right?
Yeah.
So maybe as an exercise, you can kind of verify these are the points of intersection. Yeah? Does that make sense? And the middle, like the diagonal intersects the sectors I put all the coordinates here, see? So maybe as a quick exercise, you can confirm that these are the coordinates. Yeah? Yeah, so there's really, even though there's like 6 points, there's really only 2 calculations, right? Because once you know, like, this thing here is 1 minus root 3 on 2, then you just minus from 1 to get root 3 on 2, right? And they're obviously at half. So, so basically, I think it's good to note that we want something that's slightly, remember it was like 0.26, but it was a little bid further out. It was like 0.263 or so. It was like, sorry, it was like 1, yeah, like it was, what would you say, like, it's a little bit more than 1 unit across. yeah? And so 1 minus root 3 on 2 is roughly, well, root 3 is like 1.7, on 2 is like 0.85-ish, yeah? And then minus that is like 0.15. So this is roughly 0.15 across, yeah? Yeah. So we need something, it's like 0.25 squared plus x squared, right? So x is the x value of this point, yeah? So then x is 1 minus root 3 on 2. So once you know that, you can just get the other 4 points, right? And then this one, this is the one where it's like, remember it's like the 0.4 plus, the 0.4 minus little x. So here's this 0.5 minus big X, 0.5 minus big X, are the coordinates of these points, yep. Okay, so why are the coordinates of these points helpful? Well, you need to make precise the argument that it's going to be the normal distance, right? Yeah. Okay, so what we're going to do is we're going to divide this region into 2 regions, right?
Yeah.
So it's like these 4 points is one region and these 4 points and its area is one another region, right?
Yeah.
So can you explain to me why the distances in the region is just the normal distance? Okay. So can you explain to me why the distances here is normal distance? Yeah, so if you look at the coordinates, right?
Yeah.
The coordinates are exactly, like the vertical part, this one is exactly half, that top one minus a half, yeah?
Yeah.
See that? So this is root 3 on 2 minus a half. This is root 3 on 2, yeah? And this one here is like 1 minus root 3 on 2. And this one is like 3 on 2 minus root 3 on 2. Yeah, so this is exactly half more, yeah? Okay. So basically what it's saying is like the leftmost and rightmost points are half apart horizontally, and the top and bottom most points are half apart vertically, right? So that means whenever you calculate any distances, it's going to be the same as the fractional distance. Because every distance horizontally is less than half, every distance vertically is less than half, right? That makes sense? Okay. Alright, now finish the proof. Finish the proof of the problem. Alright, so this is one of those things that you probably don't have quite enough time, but it's like, it's one of those situations where I guess if you know it's like a simple argument, you might have a better chance of finding it. But, so basically, there's the purple region and there's yellow region, right? There's 2 regions, and you got to put 3 points, yeah? Okay, can you see that means 2 of the points has to go into one of the regions? Yes? Okay, so let's just say they both go into the yellow region, okay? Yes? So if 2 points go in the yellow region, where can they go? So we want to put them as far apart as possible, right? Yeah? And so basically these regions are just like, they're just isosceles trapeziums basically, right? With the curvy edges. So the isosceles trapezium, like, it's like that, right? What's like, where's the how can you realize the diameter? Like it could be like this could be the biggest distance, right? Or it could actually, it could be that, right? And in this case, they're both the same distance, you know? So that proves, so you have to put the points either black and black or black and blue, yeah? Right? Okay. And that forces that distance to be there, right? And when you put something in this other region, like you can't put it, you can't put it anywhere. So I guess if you put it on this line, it's equally distant to both of these things, yeah? So if you want to maximize the distance, you want to probably put on in the middle line here, right? but then you'd have to put it here, and then this has the same distance. Yeah? Does that make sense? Or if this goes here and that goes here, then you're in the same problem again with the yellow, but now you're with the purple, right? You have to put it in the red point. Okay? So this proof actually also tells you what the construction has to be as well.
Yeah.
So can you see, we also proved what the constructions had to be. There's only 2 cases, right? Here there's only 2 cases as well. Does that make sense? Does anyone need like a little, do you want to ask a question?
I want to ask a question.
Yeah.
Although I've listened to 4 times.
Okay.
And my question is, how this proves the question?
Okay. So the radius of these green circles are like what is it? Like the square root of 2 minus root 3 or root 6 minus root 2, yeah? Okay.
Yeah.
So we don't want to place anything within the green circles, or it's going to have a smaller distance, yeah?
Yeah.
Okay, we're trying to put 3 points outside the green circles or on the 3 circles to get a bigger distance, yeah?
Yeah.
Okay, and we're basically proving you can't do it. You can't get a bigger distance, and the only way to get an equal distance is to put it on the green circle, yeah?
Oh.
So what
like
do we
this
have?
proves
So we have
that,
the area that you can put the 3 points, we divide into yellow and purple, right?
yeah.
So because there's only 2 areas and 3 points, 2 of the points have to go into one of the areas, yeah?
Like including the lines, right?
Including the boundaries, yeah. So without log, it's on the yellow area, right?
Yeah.
So we put 2 points on the yellow area, and we're trying to put the 2 points as far apart as possible, right? Does that make sense?
Which is either like that, or like
Yeah.
that.
So we discovered that the maximum distance we can make the 2 points is actually equal to the radius of the green circle.
Those are the
Okay,
same.
we can't actually get it bigger. Yeah?
Yeah.
And the points have to be on the green circle. So now there's no chance of you actually beating the distance already, yeah?
Wait. Is that true?
Because you can't, like, there's already 2 points that's the same distance apart as the distance you're trying to show, right? So at this point, it's already proved, yeah, once you go to construction.
Oh, that construction proves that it doesn't allow more than that.
Wait, what are you saying?
That construction allows you to prove it cannot be over 2 minus root 3.
Yeah, because now, look, you're forced to get 2 points, and one of them has to be on the green line, right? On the green intersection.
Oh, so you cannot like expand more.
Yeah, so it's already like one of the distances already squares to 2 minus root 3, so it can't possibly the minimum distance can't possibly be bigger than that.
Okay.
Yeah. And then you can continue the proof, and the rest of the proof really just tells you what the construction has to be if you don't already have a construction. Yeah.
That's the construction.
Yeah.
Like this.
Yeah, that's one of the constructions, and there's another one where it's like the black and the blue on the yellow, and yeah, and the middle point down the bottom. Oh, that probably also works. Wait, what? No, that doesn't work because of the horizontal distance between the red and the black. It's only like
No. Because it's this one is 1 minus root 3 over 2, and that's root 3 over 2. Because it's more than 0.5, I'm gonna move that to there, which is root 3 minus 2 minus 1, and these two differ by 2 minus root 3 minus root 3.
No, they don't.
No, because we're calculating the fractional distance.
Yeah, I mean the fractional distance is quite obviously just like less than. No, those two are close. Yeah, they can't use those 2 points. They're just horizontal. Like horizontal can't be more than a half. Yeah.
No. Well, we move that like one apart. So like we move this red point to one away,
Yeah.
making the fractional distance. And that distance is 2 minus root 3.
Yeah, you can't use the red point. Yeah, you can use this point here with the other 2 points.
It's 3.
Yeah.
Oh, overall we got a construct.
Yeah, so we already had a construction, but if we didn't, this proof would also force you to give only 2 possible constructions. Yeah.
Okay.
Does anyone have any more questions about this? You said something.
So this is between 2 corner points is like less than the root 3 to the red.
Which 2 corner points?
Like black and red.
This black and red.
Yeah, black and the red on the other side.
Yeah, the distance, as I was saying, it's like they're horizontal, so there has to be less than half. Yeah.
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 Yeah. Then how can anything in that shape have distance? Like any 2 points within that shape of distance more than like a half apart?
No, we're just saying. Look, like the distance from the black point to the blue point here.
Yeah.
That's got distance. You know. The distance we want.
It does.
Yeah, like 0.266 and 7 or something. So those are the coordinates. So those 2 corresponded to like the kind of like the corner things on the top and the left.
If you connect the black, the blue, the red, and the black, you get a square, no?
The what? The black?
Like the outside 4 points of that shape.
Yeah.
You get a square.
Yeah.
The longest length within the square is the...
Yeah, but the distances are different now, right?
Ah.
When you take half of it, that's when the distances are nice.
Ah.
If you take the whole thing, the distances you have to teleport. Like, do you understand the distance black to black is the same as black to blue, and it's the same as the radius of the green circle?
Oh, yeah.
Well, anyway, even if you don't know, actually, the thing is, you don't actually have to know what the distance is here, right? Because the fact it's like a trapezium or whatever, you know the distance is from either from base to base or diagonal, right?
Yeah.
And that forces it to be on the green circle.
Yeah.
Which already makes it, you know what I mean? It already makes it the same distance. It can't be bigger.
Yeah.
Yeah, so even if this distance is big, that one's definitely small. Yeah. Alright, any more questions? Yeah, so apparently this was like a difficult Q4 for China National Olympiad.
Obviously difficult before.
But I think it's actually not that bad. I think the main difficulty is just like you can't just do your old tricks. You have to investigate something.
The main difficulty is it's like not a normal.
It's like it's somewhat unconventional.
Yes, that is the difficulty.
But in terms of actual like maths, it's like primary school. You know what I'm saying?
It's like it's not.
You just don't want to jump the gun. Yeah.
Yeah. It's not a hard. It's just. It's non-standard. So.
Yeah. Yeah, so this was definitely harder than the day 1 Q1, and it's definitely harder than like IMO Q104.
Yeah. I'm on Q1.
Oh, so actually I have.
Standard.
Alright guys, dinner break.
Yay.